Hello everybody and welcome to this tutorial on electrochemistry. We're going to be talking about a few things in this tutorial. First of all, we're going to introduce you to the concept of electrochemistry and what it's all about. We're going to talk about galvanic cells in detail and how they're constructed, as well as how they're notated in written chemistry. We're also going to talk about standard reduction potentials. Now, what is electrochemistry? Well, basically, it is an area of chemistry that deals with converting between chemical and electrical energy, and vice versa. So you can have a reaction, a chemical reaction that creates electrical current, as well as you being able to induce an electrical current on a chemical reaction to make it happen. Now, this is important because the applications are in obviously making batteries and power sources and fuel cells, but in addition, it is also useful in the manufacture of plastics, such as polyvinyl chloride, when you obtain chlorine in this process. It's also used in electrical wiring to obtain aluminum and copper components for electrical wiring purposes. In addition, you can use soaps, paper textiles in this manufacturing process by producing sodium hydroxide as a main component. Now let's talk about electrochemical cells. There are two types, galvanic cell and electrolytic cell. The galvanic cell is kind of like what we had mentioned before, where it uses a chemical reaction in order to make an electrical current. The electrolytic cell enables you to induce an electrical current to stimulate an otherwise non-spontaneous reaction. Electrochemical cells use what is known as reduction oxidation reactions, or otherwise known as redox reactions. So what is oxidation and reduction? To remember what oxidation and reduction is, we use the acronym OIL-RIG, which stands for oxidation is losing, reduction is gaining. Remember, when we're talking about oxidation reduction and losing and gaining, we're talking about electrons. Notice from this example given that compound A or species A is being oxidized. Therefore, its electrons are being stripped or being taken away. So oxidation is losing electrons. Compound B is being reduced and therefore is gaining electrons. Also, you must know species A is known as the reducing agent because it is giving the electrons to another compound. Compound B is known as the oxidizing agent because it is stripping another species of its electrons and therefore gaining electrons. Okay, let's try to practice identifying whether a given reaction is oxidation or reduction. So what we're going to do is look at these half reactions. These are called half reactions because if you add them together, ideally you would get an entire reaction out of this. So let's go ahead and identify this. So we have two iodide ions yielding iodine gas, or iodine solid I mean, plus 2 electrons. Notice that the electrons is in the products, which means that this I- is giving them up, so it's losing. Therefore, this is an oxidation half reaction. So this is undergoing oxidation. If you look at the second reaction, so this is 1, 2, you have fluorine gas and 2 electrons yielding 2 fluorides. So notice that the electrons are in the reactants. They're adding to the fluorine gas. So the fluorine is getting reduced. So this is a reduction half reaction. So this is undergoing reduction. Which one's the oxidizing agent? And which one's the reducing agent? Well, the oxidizing agent is the agent that is losing, or that is stripping the other species of its electrons, right? So in essence, you can think of the oxidizing agent as fluorine gas. So this is the oxidizing agent. Be careful with oxidizing agent versus oxidation. The guy that gets reduced is the oxidizing agent. The guy that gets oxidized is the reducing agent. Okay? So be careful between those two terms. They're different. Now for part 2, it says write a balanced equation for the overall redox reaction and use the smallest possible integer coefficients. So all you have to do is take these half reactions and you want to add them together, assuming that you have equal number of electrons here. So you have 2 electrons on both half reactions. That should say 2. And you're going to add these reactions essentially. Now if you have terms on opposite sides of the arrow, they cancel out. So the 2 electrons cancel out here, leaving you with F2 iodide, iodine gas, and fluoride, or iodine solid rather, and fluoride. And that is your overall reaction. And these are the smallest coefficients that you can have, 1, 2, 1, and 2. And that is your reaction. Now if we go to the next example here, we have another electron transfer reaction. This time they give you the entire reaction, and they want you to identify the half reactions. So first of all, we need to identify which one is getting the electrons and which one isn't. And to do that, we need to identify what is known as the oxidation number, which is essentially a form of charge that it has, that each atom has. So what we're going to look at is the charge of 10 here. So we have 10 plus bromine yields 10 ion and bromide. So the charge of this 10 here is 0 because there is no charge. The charge of this bromine here is also 0. There's no charge present. Now the 10 went from 0 charge to 2. What does that mean? So 10 went from 0 to plus 2. And bromine went from 0 to minus 2. Notice that this is minus 1 here. And you have an overall of minus 2 because you have 2 bromines, 2 bromides. So essentially you went from 0 to minus 2. Okay, so the 10 lost electrons in order to get a positive charge because electrons are negatively charged, and it has a positive charge, which means it lost 2 electrons. Okay, so 2 electrons lost, and the bromine gained a negative charge, which means it gained electrons. So you have a gain of 2 electrons. Therefore bromine got reduced and 10 got oxidized. Okay, so if you were to write the half reactions, you would have 10 solid, and he got oxidized, which means he lost electrons. And you're going to have your 2 electrons like that. And then bromine got reduced. So we're going to say bromine plus its 2 electrons led to 2 bromides, aqueous. And this is your oxidation half reaction, and this is your reduction half reaction. It's pretty straightforward. And then if you were to add all these together, notice that the electrons cancel out and you get your overall reaction over here that the problem gave us. So this is indeed correct. Okay, in order to deal with oxidation-reduction reactions, we need to know how to balance them. So there are 2 conditions in which you can balance these oxidation-reduction reactions. You can reduced them or balanced them under acidic conditions or basic conditions. Now, the acidic and basic conditions have the same steps, except that the basic conditions have an extra step at the very end. So we're going to look at acidic conditions first. The first step that you want to do is assign oxidation numbers, sort of like the previous example where we looked at oxidation numbers in order to determine how many electrons were transferred and what was reduced. Second step, you want to separate into oxidation and reduction half reactions, also like we did in one of the previous examples. Then you want to balance all the atoms. So first of all, you want to balance all the elements that are not oxygen or hydrogen. You only want to balance non-oxygen and non-hydrogen atoms first. Once you do this, you can balance the oxygen by adding water. So if you need 3 oxygens, you would add 3 waters. Then you would proceed to balance the hydrogens by adding hydrogen ions. So if you have 6 hydrogens on one side, 3 on the other, that means you only need 3 on the side that has 3 hydrogens, and you would add 3 hydrogen ions to that side. You also want to balance the charge by adding electrons to whatever side needs it. So if, for example, you have a neutral charge on one side and you have a +2 overall charge on the right side, then you would add 2 electrons to the right side so that both sides are neutral. Next, you want to go ahead and under basic conditions. So if you were in acidic conditions, you would be done after adding the hydrogen ions. However, if you're in basic solution, you need one additional step. You need to add the hydroxide ion to whichever side has the hydrogen ions. So if you have 6 hydrogen ions on one side, you want to add 6 hydroxide ions in order to neutralize this and turn it into water. Once you have water, make sure that you cancel out any sides to have water on both sides. So for example, if you end up having 2 waters on one side, 4 waters on the other side, you want to make sure that they cancel out so that you only end up having water on just the one side. And this is basically the simplification. All you have to do at this point now is add the half reactions together once they are balanced properly, and you would obtain the overall reaction. If at this point you need to reduce the coefficients, at this step you can go ahead and reduce the coefficients. For example, if you have 2, 4, 6, 2, then you can divide each of those coefficients by 2 and you will be done. So let's go ahead and do an example right here. So they give us what is called the skeletal oxidation-reduction reaction, which is a basic, bare bones reaction and not balanced in any way. Charges aren't balanced, or charges don't necessarily have to be balanced. It's just a reaction. So we're going to go ahead and balance this, and we're going to do it in acidic conditions. So let's go ahead and get started. So remember that the first step is to determine the oxidation numbers, right? So notice that nickel has a +2 right here, +2. Now to determine oxidation numbers for chlorate, which is right here, let's go ahead and write that out. So we have chlorate. The overall charge of chlorate is -1. The charge for oxygen is almost always going to be -2, because if you look in the periodic table, it needs 2 electrons to get to the next noble gas. So it's going to want to have 2 electrons most of the time. Notice that you have 3 oxygens though. So overall, you have a -6 charge. So we need to determine what is the charge of chlorine in order to make the overall charge -1. So we're just going to set up an equation. X plus -6 equals -1. Notice that X has to be 5 in order for this equation to be true. So therefore, chlorine is going to be +5. So we're going to say that chlorine here is +5, and oxygen is obviously -2, overall -6. Notice that nickel on the product side is 0. There is no charge. Now if we look at chlorates or hyperchlorate or perchlorate, overall charge is -1, oxygen is -2, overall is -8 for oxygen. So X plus -8 equals -1, therefore X has to be 7. So the charge of chlorine here is +7. So notice that nickel went from +2 to 0, and chlorine went from +5 to +7. Nickel gained 2 electrons, so this is a gain here. Or he got reduced. The way I think of reduced is if the number reduces or gets smaller, it's reduced. So it went from +2 to 0, which means that the number got reduced or got more negative. In the case of chlorine, it increased. It did not reduce, so it's going to be oxidation by default. So this got oxidized, and nickel got reduced. So now we know which one's the reduction and which one is the oxidation. So we're going to go ahead and write those out. So we have nickel plus 2 electrons gives us nickel plus 2. And we have chlorine got oxidized, Cl2 got oxidized to 2 chlorides and 2 electrons. Oops, I'm sorry. I don't know why I wrote that. It should have been chlorate. Apologize for that. So chlorate. The chlorine did get oxidized, but we need to use the entire compound. So chlorate got oxidized to perchlorate, and you have your 2 electrons. Okay, so we're going to go ahead and erase everything else here. Okay, so we have our 2 reactions, or 2 half reactions, correct? So now we're going to proceed with the next step, which is to balance any of the non-hydrogen and non-oxygen atoms. So we're going to first balance the nickel. Notice that you have 1 nickel on each side, so you're good as far as balancing that. For the second half reaction, you have 1 chlorine on both sides. You have, and that's it. So the chlorine is balanced. Now you're going to go ahead and balance any oxygens or hydrogens you have. The first half reaction is done. There is no hydrogens or oxygen, so we're done with that. The second one, however, notice that there's 3 oxygens on the left side, 4 on the right side. So that means we're missing 1 oxygen. Okay, so, and note that we don't really have to write the electrons here until the very end. You can balance this in a later step, so don't worry if you forget the electrons. Okay, and on another note, so let's go ahead and add in the 1 water molecule because we need 1 more oxygen. So now we have 4 oxygens on each side. So we're perfect on that. Now, however, we added 2 extra hydrogens on the left side that we need to balance on the right side. So we're going to add in 2 hydrogen ions on the right side. Now everything is balanced as far as hydrogen and oxygen. So then we're going to go ahead and proceed to add the reactions. But first, before we do that, let's see if the charges are balanced. So we have a -1 on this left side, and we also have a -1 on the right side. So we're perfect. We don't have to add any other extra electrons. If you needed to add any extra electrons, you can go ahead and do so at this step. But right now we're balanced. So we can go ahead and add these reactions. So let's go ahead and add these reactions. I'm going to add these reactions over here. So we have a nickel, and notice that the electrons cancel. We have the chlorate ion, we have water, we have perchlorate, we have nickel plus 2, and we have 2 hydrogen ions. So this equation is balanced under acidic conditions. Now if you wanted to do under basic conditions, you would go ahead and add in 2 hydroxide ions here and eliminate any water molecules that may be present. However, we're only doing acidic conditions for this problem. For the next problem, we're going to look at chlorate going to chlorine. So again, we're going to look at the charges. So 0 went to +2. So that means 10 got oxidized because the number got increased. It didn't get reduced. Since the number didn't get reduced, it got oxidized. So 10 got oxidized. And then we're going to look at the chlorine here. Remember, overall for chlorate is -1. Oxygen is -2. -2 and 3 make -6. Chlorine has to be +5 in order to make it -1. So chlorine went from 5 to, in this case, chlorine, there is no charge there, so it's going to be 0. So it went from +5 to 0. So the number got reduced. So therefore this is a reduction. Okay, now, so we're going to go ahead and write out the reactions. We don't have to write the electrons at this time. We don't have to. And in fact, I won't, in order to show you that you can do that. So we're going to go ahead and say that 10 went to 10 plus 2, or 2 plus. And then we'll add in the electrons at another step. So now we went chlorate turned into chlorine gas. Remember the first step, once you write the reactions, is to balance the non-hydrogen, non-oxygen atoms. Notice there's 1 10 on each side on the top reaction. For the bottom reaction, we have 1 chlorine on the left side, 2 on the right side. So let's balance that out. So I'm just going to go ahead and write in a 2 in front of it. Now we have 2 chlorines on the left side, 2 on the right side. Now we need to balance oxygens. So we have 6 oxygens on the left side now, because 2 times 3. And so we need to add in 6 waters to the right side. However, now that made 12 hydrogens that I need to balance on the left side. So we're going to add in the 12 hydrogen ions on the left side. Sorry, that should be 12. Okay, so now that we finished that, we're going to look at the charges and see if they're balanced. So on the left side we have +12 and -2. Remember, because there's a 2 and then there's a negative, so that's going to be -2. So technically there's a charge of +10 on the left side. And on the right side there's a charge of neutral. Therefore we have to add in 10 electrons on the left side in order for this to balance, correct? So we need to add in 10 electrons. So I'm going to go ahead and add in 10 electrons to the left side. Let me go ahead and erase all these here. So for the top reaction, let's go ahead and balance the electrons, the charge. There's a +2 on the right side, 0 on the left side, so we're going to go ahead and add in 2 electrons to the right side. And therefore, now we added in the electrons, so we're good. We should be able to add this reaction now. However, notice that you have 2 electrons on the right side for the top and 10 on the left side for the bottom. Those have to be the same in order for them to fully cancel out. And you want the electrons to cancel out when you add the reactions. So what we're going to do is multiply the top reaction by 5. And that will make this 10 electrons. Now we can go ahead and add the reactions together and the electrons will fully cancel out. So those completely cancel out. So adding them together gives you 12 hydrogen ions, 5 10, 2 chlorates, another 5 10 ion, chlorine gas, and 6 waters. And that is your overall redox reaction balanced under acidic conditions. Okay, so we're going to work another balancing redox reaction example, except we're going to do this under basic conditions. So remember that the steps are very similar to acidic conditions, except for that one extra step in which we add in hydroxide ion to neutralize all of the hydrogen ions. Okay, so let's go ahead and write down the reactions. We're going to skip the oxidation, the oxidizing or the oxidation numbers step, because we're just concerned with balancing the reaction, and you'll see that everything will come to place as soon as we balance this. So we really don't have to assign oxidation numbers per se, unless they want you to. So we're going to go ahead and write out the two half reactions, no electrons. We'll do those at the very end. So we have chromium hydroxide going to chromium, and you have sulfide going to sulfur. So notice that the sulfurs are balanced and the chromiums are balanced. So we don't have to do that at all. For the oxygens, there's 3 on the left side, so we need to go ahead and add in 3 compounds of water. Now there's 6 waters on the right side, 3 on the left, or 6 hydrogens on the right side, 3 on the left side. So we're going to go ahead and add in 3 hydrogen ions on the left side. Now we're going to go ahead and balance charges. So notice that there's a +3 on the left side for the top equation, and neutral on the right side. So we're going to go ahead and add in 3 electrons to the left side to balance it out. For the sulfur equation, there's a -2 on the left side, a neutral on the right side. So we're going to go ahead and add in 2 electrons to balance that out. Now remember the extra step. The extra step is to add in extra hydroxide ions to neutralize all of the hydrogen ions. So we're going to add in 3 hydroxide ions to both sides of the equation. The hydrogen ions and the hydroxide ions become water, 3 moles of water. So let me go ahead and erase this now. Okay, so we have 3 waters. Okay, so now notice that there's 3 molecules of water on each side here, so they essentially cancel out. Now everything else should be balanced. We should be able to add the equations as long as the number of electrons are equal, which they are not. So we need to make them equal. So we'll multiply the top equation by 2, the bottom equation by 3. So we have here 2 chromium hydroxide, 6 electrons, 2 chromium solid, and 6 hydroxide. For the bottom, we have 3 sulfurs on each side and 6 electrons. Now we can go ahead and add the chemical equations together. 6 electrons cancel out completely, leaving us with 2 chromium hydroxides, 3 sulfides, 2 moles of solid chromium, 3 moles of sulfur, and 6 hydroxides. So now you can go ahead and verify that this is the balanced equation by looking at the charges. The left side, the charge overall is -6. The right side, the charge overall is -6 as well. There are 6 hydroxides on each side, 2 chromiums, and 3 sulfurs. Now this is another example of a basic equation. Let's go ahead and do this one. So we have chlorine going to chloride. We have bismuth becoming bismuth hydroxide. Notice that for the top we need to balance the chlorine here. So there you go, that's balanced. Bismuth, there's 1 on each side, so that's done. Hydroxide, there's 3 oxygens on the right side, so we're going to add in 3 waters on the left side. Now there's 6 hydrogens on the left side. We'll add in 3 hydrogen ions there. Let's balance the charge. Plus 3 on the right side needs to be neutralized. So now it's the bottom equation is the same charge on each side. On the top equation, we need to add in 2 electrons here in order to balance the -2 charge on the right side. Again, since we're doing basic conditions, we're going to go ahead and add in the hydroxide here to neutralize all of the hydrogen ion. Notice that waters also cancel out. This makes 3 waters, which cancels out perfectly with that. And we need to multiply the top by 3 because we need to have 6 electrons. So in the bottom, we need to multiply by 2. 6. Actually, the waters cancel out. Now the electrons fully cancel out, and we can go ahead and proceed to add the equation. So we have 3 chlorines. We have 6 hydroxides, 2 bismuth, 2 bismuth hydroxides, and we're missing something else. Oh, we're missing the 6 chlorides. Okay, so there's 6 chlorines on each side, 2 bismuth atoms on each side, 6 hydroxides, -6 charge on the left side, -6 charge on the right side. So this is perfectly balanced. And that is your answer. You will notice that most, if not the entire video, or the rest of this video, is going to focus on galvanic cells and their reactions. But what are galvanic cells? We're going to talk about it by doing an illustration of a specific type of redox reaction, the copper-zinc redox reaction. So let's go ahead and write down that reaction. We have solid zinc plus copper ion yields zinc ion and solid copper. So let's take a look at this reaction in detail. Now you may be able to make a beaker and fill it up with, say, a solution of copper, let's say copper chloride. In this manner, you have copper ions floating in solution and chloride ions floating in solution. And you can, and let's say we put in a solid piece of zinc and dip it into this solution. Now what's going to happen is that this redox reaction is going to take place. The zinc is going to lose electrons, go from neutral to +2, so it's going to lose 2 electrons, and those electrons are going to transfer to the copper, therefore making solid copper. So in this case, you're going to see a deposit of solid copper onto the metal. And that is because of this electron transfer. Now, after a while, this reaction will cease because there's only so much zinc that is exposed, and there's only so many electrons that can go to that transfer to the copper. However, let's say you wanted to convert this electrical energy and use it to power something up, say a light bulb. Well, what you'd have to do is construct a cell called a Daniell cell. Now this cell involves two beakers, and these beakers will be called half cells. So let's go ahead and draw that. Let me just draw that real quick. So we're going to have 2 half cells, so we're going to have 2 beakers here. each filled up with their own solution. Now we're going to have solid zinc here, and this beaker, these are half cells, so that's one half cell, that's another, and this solution is going to be filled with zinc chloride, and we're going to put a solid piece of copper here and fill that up with copper chloride. Okay, so now what we're going to do is we're going to link these two half cells via electrical wiring, and this electrical wiring itself is going to connect to, say, a light bulb. Now, what is the direction of electron flow? Well, we know that the zinc is being oxidized, so it's being stripped of its electrons. So the electrons are going to transfer in this electrical circuit through the wire and power this light bulb, and then it's going to transfer to the copper metal, which is then going to transfer to the copper solution. So therefore you're going to see solid copper deposits on here. Now what's going to happen is that if you connect these two half cells together, you're going to essentially get a buildup of charge on both sides, and the current will stop flowing. This current here will stop flowing, and that's because you have an imbalance of charge. After a while, all this charge is going, all these electrons are going to the right side, and therefore it's making that side less positive or more negative. And the left side is going to become more positive, and therefore this electron flow is not going to happen anymore. So in order to complete the circuit and prevent that from happening, we're going to add a bridge here, and we're going to call that a salt bridge. A salt bridge essentially completes this circuit so that it's one full closed circuit. And in essence, basically the salt bridge contains, we're going to say, potassium chloride. So it's going to contain ions that are relatively inert and do not participate in the reaction per se. What these ions do is basically they help migrate ions in order to balance the charge. So if electrons are going to the right side, that's going to make the solution more negative. So you're going to see, for example, potassium ion going in that side in order to make it more positive. In the case of the left side, it's going to become more positive, so you're going to have the chloride ion traveling there. So basically it serves as a method of travel so that the ions and the charges can equilibrate. Now, the right side here is known as the cathode, and it's the positively charged. And the way you can remember this is that the cations move towards the cathode. And when I mean by cations, I mean the potassium ions. So this zinc ion is going to want to move to the right side, as well as the potassium ion moving to the right side, in order to make that side more positive, to make up for the fact that the electrons are going there. So therefore these cations are moving towards the cathode, and hence that's why it's known as the cathode. Now, as far as the anions are concerned, they're moving towards the left side, and that left side is the negative side, and it is known as the anode because the anions are moving towards the anode. So in this case, the chloride and the chloride is moving towards the left side, and it's moving towards the anode. The anode serves as a source of electrons. Now, and this is essentially the circuit. Now, how do we know whether the electrons go from zinc or from copper? Well, we're going to be studying standard reduction potentials and analyzing half reactions to determine what is their charge, or what is the voltage or potential for each half reaction, and that will determine what directions the electron flows in. Now, I know that the electrons flow from the zinc because this is a standard experiment. However, we'll be doing problems in order to determine what direction the electron goes depending on what the voltages are or the potentials. Okay, now that we talked about galvanic cells, we're going to illustrate the notation for these galvanic cells. So right now we're going to look at the reaction that we looked at last time, and remember that for this reaction we drew the Daniell cell like this with your salt bridge, your zinc solid, your solution of zinc ions as well as chloride, your solution on the right side of copper ions as well as chloride, and your solid copper. So how do we notate this? Well, basically the way we write it is we start with the anode on the left side and the cathode on the right side. So we're going to start with zinc solid, and then we're going to use a vertical bar like this. This vertical bar denotes a phase boundary. A phase boundary is a boundary between between materials of two different phases. In this case, we're going to separate the zinc from its zinc ions. And then we're going to use two vertical bars, which denotes the salt bridge here. And then we're going to write in the copper ion. These are both aqueous. A vertical bar to separate the copper ion aqueous phase from the copper solid phase. Now we always put the reactants first. So that's the reactant for the anode, and then this is the reactant for the cathode. And then the products go after. Now remember, anode first, then cathode. Essentially, if you picture this as two cells, this is your beaker 1 and this is your beaker 2 separated by the salt bridge. Pretty easy if you think about it that way. Or you can think of it as two separate half reactions. Zinc solid yields zinc ion and 2 electrons, because remember it gets oxidized. Now another way to remember oxidation and anode is that anode is starts with an A, and A is a vowel, and so does oxidation. So oxidation starts with an O, which is a vowel. So they're both vowels, so anode is oxidation. Cathode is reduction. Those both start with consonants. So the cathode is the reduction half reaction. So in this case we have the copper ion plus the electrons yields copper solid. So in this case, if you look at this first reaction, it's simply this. And then so you basically write the oxidation reaction separated by salt bridge, and then the reduction reaction. And you basically have your notation. Okay, so we're going to go ahead and look at our zinc copper ion reaction yet again. However, now we're going to determine why the zinc got oxidized and why the copper got reduced. And why is this reaction the way it is? Why isn't it the other way around? Why doesn't the copper get oxidized? And we're going to look at that. In order to determine if this reaction happens or not, first of all, we need to look up a table of potentials, okay, which are essentially voltages. So if you go to this table here, and this is a very standard table of reduction potentials. Notice that if we look at the chlorine, or not the chlorine, the copper, so let's go ahead and scroll down to zinc here. So we have zinc right here. And we also have copper right here. So if you look at those voltages or potentials there, remember that these are reduction potentials. So that means that this is the potential that it takes to be reduced. So the reduction potential for zinc is negative 0.763 volts. The potential reduction for copper is 0.337 volts. Okay, so essentially this is telling you that copper wants to be reduced and zinc does not want to be reduced. So if you see a negative potential, that indicates that it really does not want for that to happen. So in this case, since this is a table of reduction potentials, this is telling you that zinc does not want to be reduced, but copper does. So copper wants to be reduced relative to zinc. So in this case, if you are higher up on this table, this means that you want to be reduced. The reference for this is the hydrogen electrode, and we just denote that by 0. Everything else that is above that wants to be reduced relative to that, relative to the things that are below that reference. So if we go back, let's go ahead and write down those potentials. So the potentials for copper, let's go ahead and write that down. So the reduction potential for copper was 0.337 volts, if I'm not mistaken. And then the reduction for zinc was negative, let's go back down to it, negative 0.763 volts. Now to determine the potential for the entire reaction, all we have to do is just add in the reduction, the potential for reduction plus the potential for oxidation. That's all we have to do. So just add those two potentials. Now we know from this reaction here that the half reactions are zinc yields zinc ion and 2 electrons, so that got oxidized. So since we know that the reduction for zinc is this, all we need to do is flip the sign to positive in order to let it reflect oxidation, because remember the table only gives us reduction. So if we want oxidation, all we have to do is flip the sign. So now the oxidation here is going to be positive 0.763 volts. Now if we look at the other reaction, this is a reduction half reaction. Copper gets reduced. So therefore we use the value that is in the table, which is the 0.337 volts. Now you're going to proceed to add these two potentials. And you're going to get a potential that is greater than 0. Okay? So if you get a potential for the reaction of greater than 0 or positive, this indicates that this is spontaneous. And basically it indicates that it will want to take place. So in this case, zinc will want to be oxidized by copper, which gets reduced. So zinc here, recall what oxidizing and reducing agents are. Zinc here is the reducing agent because it is being oxidized. And copper is the oxidizing agent because it is getting reduced. Or rather, copper ion wants to be reduced, right? So in this case, this is a favorable reaction. And this is how we can tell. If we reversed it, notice that, let's say we reverse this reaction and we have zinc ion. Let's say we went this direction. We went zinc ion and copper. Will that reaction want to take place? Well, if you look at it, zinc is now being reduced, right? So the reduction for zinc, this is going to be negative 0.763. Okay, so we're going to write that over here, negative 0.763. That's going to be the new reduced now. For oxidizing, it's going to be negative 0.337 because now copper is being oxidized, right? In that case, this will flip sign and become negative. So you're going to have negative 0.337. So essentially, if you want to reverse the direction, you just flip the sign of the E of the potential for the reaction that you found earlier. So notice that this is going to be less than 0 and therefore is not favorable. Okay, we're going to go ahead and apply all of the concepts we learned thus far. So we're going to apply basically the concept of the half cells, of the electrodes like anode, cathode, and such. So it says here that we have the following voltaic cell constructed with the following reaction: tin and aluminum. And what is the cathode reaction and what is the anode reaction? So let's go ahead and answer that first. So we have tin going from a +2 charge to a 0 or neutral charge, correct? So it is getting reduced. The number is getting smaller. Reduced is R, and R is a consonant. And remember the little trick that I showed you, that consonant goes with consonant, so therefore cathode is what explains this. So therefore the cathode reaction is the reaction with zinc plus 2 electrons yielding solid zinc. I'm sorry, not zinc, tin. So the reaction is the tin being reduced. Okay, so cathode is reduced. Or you can think of cathode as the positive side. So therefore, remember, so the cathode is the positive side, and the electrons go from negative to positive, which would explain why they want to move towards the cathode and why the cathode is reduction. Now the anode reaction is going to be the aluminum reaction, where aluminum is being oxidized. Remember, anode starts with a A, and A is a vowel, and so does oxidize. So therefore anode is oxidation. So aluminum is being oxidized to aluminum ion, and there's going to be 3 electrons. Now if they were to ask how many electrons in total were transferred between the two, it would be 6 electrons, because if you look at here, we have a total charge of +6 for the tin, because we have 3 tin ions, and +6 is going to 0, so therefore it's a total of 6 electrons that are being transferred. Okay, so if they were to ask that, the total electrons transferred would equal 6. Now let's look at the next question. In the external circuit, electrons migrate from, let's take a look at this menu. It says from or to the electrode, the tin electrode. Now we said the tin was, we said that the tin electrode was the cathode, right? So remember, electrons want to go from negative to positive, cathode is positive, and therefore it wants to move to the tin electrode. Or you can think of the tin electrode as being reduction, and therefore the electrons go there to reduce it. And then it says this is going to be from the aluminum electrode. In the salt bridge, anions migrate to or from the aluminum compartment to or from the tin compartment. So remember that, let's go ahead and just draw it out real quick here. So we have this half cell, this half cell, you have your salt bridge. We said that the aluminum, or I'm sorry, we said that the tin was the cathode. So we're going to say that this is the aluminum, this is the tin. So the tin is the cathode, which is positive, the aluminum is negative. So negative is a source of electrons, so electrons is going to go towards the tin. Now, since the electrons are going towards the tin, it's going to make this side more negative, and therefore we had to have cations moving towards that direction in order to neutralize that negative charge. Similarly, the aluminum side is going to be more positive because electrons are leaving it, so the anions from here have to move here in order to neutralize that positive charge. So therefore the anions migrate to the aluminum compartment from the tin compartment. Okay, let's go ahead and do another example of this here. So we have a voltaic cell constructed, and you have, let's go ahead and write this out. So you have so you have your anode, salt bridge, and your cathode. Now let's see if this makes sense. First of all, I drew it like this, but let's see if this notation makes sense. This is the anode, supposedly. That's what they said. And the anode is the negative charge, so that's the source of electrons. So that is going to be oxidation. So therefore, we have to write this like this. So we have, this is the source of electrons. So you're going to have two iodides making iodide and two electrons. So that is indeed oxidation, so this is correct, the left side. Now let's look at the right side. That should be reducing, right? So it should be this plus two electrons yielding two fluorides. So the way I wrote this here is incorrect on the right side. So I just wanted to illustrate that to make sure, to help you determine whether a given notation is correct or not. So in this case, it should be your solid phase, and then you're going to have your ion phase there, your aqueous. So this makes more sense. The right side is cathode, which is reduction, and the left side is anode, which is oxidation. Now, so that's your notation. Now it says here that the compartments are connected by a salt bridge. Use the lowest possible coefficients. So let's go ahead and find out what the anode reaction is. We kind of just already mentioned that. That's this reaction here. So that's your anode. Your cathode is this reaction here. Now they want the net reaction. The net reaction is simply the sum of these two reactions. So we're going to sum them up, and notice that the electrons cancel out if we add them up. And you get two iodides plus fluorine gas yields iodine solid plus two fluorides. And that is your overall net reaction. In the external circuit, the electrons migrate from or to the fluorine to and from the iodine electrode. Now we said that the fluorine electrode is is the cathode. It's getting reduced. So the electrons want to migrate to where it wants to reduce, right? So it wants to migrate to the cathode, so it's going to be to that electrode from the iodine electrode. In the salt bridge, the way to remember this, the anions migrate to the anode. That's why it's called anode. So therefore the anions migrate to the anode, and the anode is iodide, so it wants to migrate to the iodide from the cathode, or the fluorine. Okay, let's do one more example, just to make sure that you understand this concept of anodes, cathodes, and half cells. And we're also going to calculate reduction potentials here, since we talked about that. So let's go ahead and do the anode reaction real quick. So so we're given a voltaic cell constructed from manganese and chromium. Now we need to determine whether the manganese is being reduced or oxidized, and as well as the chromium. So we need to determine which is going to be the advantageous combination. Is it better for manganese to be reduced or oxidized? So we're going to determine this. So remember that we want the potential for the cell or the reaction to be. Let's go ahead and erase this here. We want the potential for the reaction okay, so Sorry about that. I just had to erase that real quick. So basically, we were saying that if we want we want the potential for the reaction to be greater than 0 or positive in order for the process or the chemical reaction to be spontaneous or to want to take place. So in this case, we need to use this combination in order to make it positive. Now I noticed that if I get this to be reduction, which is negative 0.740, and then I flip this to positive 1.180, meaning that it now becomes oxidation, then if I add those together, I will get a number that is greater than 0. Sorry about that. It should be 1.180. Then I will get a potential that is greater than 0. If I did it the other way around, where I had negative 1.18 and then positive 0.74, that's going to give me less than 0. So I know, so basically this is telling me that manganese wants to be oxidized in this case, and that chromium wants to be reduced. So that's what it's telling me. So therefore I have to flip the sign for this one, the reduction for the manganese one, and I'll just keep the chromium constant, just the way it is, negative. Okay, so let's just go ahead and answer the voltage while we're at it. So we're going to say that the voltage, the reaction voltage, or the cell voltage, same thing, is going to be your oxidation plus your reduction. And in this case, the oxidation, we said that was going to be the manganese, because that would be 1.180 plus negative 0.740. Now if we went ahead and typed that in on a calculator, let's go ahead and pull that up here. 1.18 minus 0.74, and we're going to get 0.44. Okay, so let's go ahead and write that, 0.44 volts. So that's going to be the answer here. So the answer here is 0.44 volts. Okay. Now we're going to go ahead and write the spontaneous cell reaction. The spontaneous cell reaction is basically where manganese gets oxidized. So manganese is going to be oxidized. Let's go ahead and actually do the half reactions first, because that'll determine our spontaneous reaction. So this is going to be anode, and remember the anode is oxidation. So we're going to have manganese being oxidized to manganese ion, and we're going to have 2 electrons there. So that's our answer for the anode here. For the cathode, we have the chromium being reduced. In this case, there's going to be 3 electrons in order to reduce it to chromium. So those are your half reactions. Pretty easy. Now we're going to put them together. So let me go ahead and write them both over here on the side. So we have manganese ion, 2 electrons. Now we're going to multiply the manganese by 3, because we want that to be 6 electrons, so that when we add these electrons together, they'll cancel out. So this is going to be 3, 3, 6. And for the chromium one, we're going to multiply by 2 in order to get 6 electrons there. And 2 chromium solid. So now the electrons cancel out, if you notice. And then you're going to get a net reaction of 3 manganese solid plus 2 chromium ions aqueous yields 3 manganese ions and 2 moles of solid chromium. And that is going to be your chemical reaction. So in this case, your chromium is your cathode, it is being reduced. Your manganese half cell is your anode, it is being oxidized. And your voltage is 0.44 volts, so we know it's favorable. And it won't be favorable if we reverse the direction. If we reverse the direction, the voltage will be negative 0.44 volts.